welcome to day 7 of 12 days of DevRel at Hazelcast. Thank you for tuning in for part 2 of 14 golden rules of using Hazelcast with Neil Stevenson. Make sure to leave your questions in the comment section below and also sign up for the link on the screen now to get notified when we go live. Now, sit back, relax, and enjoy part 2.
Which comes us to rule number 6. Odds beats evens. What does that even mean? Hazelcast is a distributed system. How many times am I going to say that? But it runs on multiple machines connected on networks. And if we were to say that firewall rule, what happens if the network fails? And it hasn't really failed. Just remember, firewall is doing the right thing. Just it was a bad rule. So that can give you a thing which in distributed systems is called a split brain. Your clusters split into the left half and the right half for the sake of argument, or whatever way you want to think of them. Everything is running, so it's not like the host failure situation, but the right half can't talk to the left half, so it really doesn't know if the right half is running or not. So it's no different than if those hosts have failed. And the flip side is, the left half doesn't know about the right half, so neither knows. And what do you do then? How do we cope with this? And, well, if you want to read up on it, look for a thing called the CAP theorem. So CAP theorem is basically what do you do when your cluster splits? And you can be A in that partitioning event, which means available, or you can be C in that partitioning event, which means you can be consistent. A data object is either available or consistent. You can't have both, unfortunately, but Hazelcast does provide both options. You just need to choose what you want to be. So if what we're saying is available, then your cluster split in two. You can change your data in left and right, the same data record, and the data record deviates, and somehow you merge them together when the network problem is resolved. Or you can say, well, we'll not allow them to deviate because we don't want them to. You choose. We provide the options, you make the choice. And why odds beats evens? So we mentioned earlier, the left half doesn't know about the right half, and that's because they're halves. So if your cluster was 140 nodes and you split it in two, you've got 70 and 70. So the right 70 doesn't know about the left 70. What deductions can it make? Nothing at all. If it was that 3-node cluster and the network breaks, you've got a 2 and a 1. So the 1 doesn't know what's happened to the 2s, but it does know that it is the smaller, and the 2 doesn't know about the 1, but it does know it is the bigger. So it could decide, well, I'm the majority, I will do something. I'm the minority, I will shut down or whatever I want to do. So you can make a deduction if you have an odd number, because you can always know who's the biggest. So the point to that is don't go for an even number. Don't go for an even number of machines, because the network split is between machines. So think of it like this, that if you had a cluster on 5 hosts, then it might break as 3 and 2 or 4 and 1, depending where you kind of slice. And the bigger half, the bigger part can make a majority decision because it knows it's the majority. It doesn't know the state of the other things, but it can make that decision without knowing that. I will say here that we also recommend it's 1 Hazelcast per host. If for some reason you deployed 2 Hazelcasts per host and it was 5 hosts, then you've got 10, and the way that splits, it's a network split, it would be 6 and 4 or 8 and 2. It's still the same, because it's the network card that's not giving you the response you want. So pick an odd number. Which brings us to CP, the consistent in partition event option in Hazelcast. Hazelcast started life as AP, so if your data is huge and you want to stretch it across multiple machines, then that is an AP system. It's available, but your data is spread across 140 machines. That is where CP came in, because there's certain things that you don't want to break in a networking split. And that's where you want the CP, the consistency. So CP is using the Raft consistency algorithm. Basically, you make a change, you might have five CP processes. The change is committed when you get a majority of responses. Most of us have done it, therefore we know we're in a consistent state. It's Raft algorithm, you can read up on it if you like, and it gives provably correct access to your data in partitioning events. So you split your cluster, you might have a CP group of 3 or 5 or 7, those are the allowed sizes, because that's odd beats evens. And you might have a group that runs on nodes 1, 2, and 3, and another group that runs on nodes 2, 3, and 4. And you can have CP objects in that subset of machines. So a CP object might be something like an atomic counter. So you have an atomic counter, it's held across 3 machines. Every time it changes, there is a consensus as to what the current value is, and that's fine. And you might have another atomic counter in a different group, and again, the same consensus works. That consensus comes with a performance cost, which is why you kind of limit it to 7 as the upper limit. I mean, it could be 9, it would just perform worse, and we like performance. So think of it this way, Hazelcast is designed to kind of take a hit, but it's not indestructible. So that 3 and 2, 4 and 1 split, if there are meaningful operations, you can keep going. And that's for that firewall rule thing, which is the most common. But there's other ways that could split, firewall rules could be always, and you could split all sorts of different factors, 4, 3, 1, 1, and 1. And is that likely? And, how indestructible do you want it to be? It's back to the data center fire. You have to accept that that could happen and just totally trash everything, and that's why you need another data center. So split brain is a networking thing that affects hosts, and you can't stop it. And if you've got an even number of machines, you've made it worse for yourself. And if absolute consistency is a thing, that's maybe when CP is your solution. So it will run an odd number of CP processes, even though you may have an even number of machines. Rule 7. We mentioned earlier 3 is the minimum supported, and I vaguely hinted at 2 not being a great idea. In fact, 2 is the worst, really. And the reason we want to get this in is a lot of people run a 2-node Hazelcast cluster, and that's running with scissors towards a wall. That's going to go wrong. Trust us, or don't trust us. Just wait until it fails, and then you'll understand. Because we're talking about clustering, or Hazelcast is a distributed system. You've got, 1 isn't a cluster, obviously. If you've got 1 node and it fails, that's it. You've lost your entire service. So a lot of clustering products go with 2. For a few reasons we're going to list, that's not good for Hazelcast, because it's important you understand. And I think it's actually true for a few other clustering products as well. So I'm not sure that 2 is actually a good answer for other tools as well. So first of all, you don't get any increase in capacity when you go from 1 Hazelcast node to 2 if you've got the default settings. So the default setting, as we mentioned earlier, is like there's a backup count. So I create a data record, and I put that in my only node. I can't have a backup because I've only got the one node. So that's fine. And let's say that data record is huge and that's all that node can store. That'd be a little bit unlikely, but let's just say for the sake of argument. If I have two nodes and backup count of 1, so there's 2 copies, we've got that huge data record in node 1 and the backup copy now is in node 2. So you don't get any increase in capacity. You do get an increase in resilience because now you've got that backup copy, but that big backup is filling up the second node. So you haven't gained anything in terms of capacity. It's not until you would add a third node. So 2 nodes with the default setting doesn't give you any extra capacity. Now you can turn backup count off, and then that's once you start, that means you've got no protection for that data record, which might be fine depending what it is. If it's something you can easily recreate, or it doesn't matter if it's lost. But that's kind of getting into more detailed territory. So the default, the capacity doesn't change. So that's not a great thing. This one's really surprising for people. Performance decreases. And it's like, well, if we had that one node and you write that data record, you write that data record. If you've got 2 nodes and you've got the backup, you've got to write the data record and communicate to get backup done. So it's a little bit extra work. So performance goes down. And again, counterintuitive, but when you see it explained like that, suddenly it's, yeah, 2 is a pretty stupid idea with that backup count. So we're getting worse performance, no increase in capacity. And just to make things even worse, now we've got 2 nodes, we can have that split. So, we're just loading this up with things that we hate. And 3 out of 4, what do you think number 4 is? We mentioned resilient. Well, really, is it? So we've got those 2 nodes and we lose one of them. Well, we haven't lost our data record. But now we've got 1 node instead of 2, so our processing capacity is halved. We're presuming that everything is still accessing this at the same rate, and your processing capacity is halved. Will it cope? Will you meet your SLAs? This one's a bit more vague. I mean, definitely, it's your mileage may vary, but it's for that reason it's not a good idea to do. So 2 is a bad idea. If your sizing has come out with 2 and you don't have enough money for 3, you may as well go with 1. I mean, in all cases, we would not recommend 1 or 2, but we're just saying, don't think that 2 is automatically better than 1. So because of all those reasons, and if your sizing says 2, go for 3. 3 is a proper cluster of a distributed system. That's the key thing. So rules 1, 4, and 6. 3 is the minimum supported size because of various things, but also remember serialization and your split brain and all the kind of other considerations. 3 minimal. So on to rule number 9 now. Sizing is a little bit of a fallacy. Right at the start, we had the string hello, and I said it's not particularly big. Well, how big is it? And it's like, well, 5, obviously. And it's like, no, not actually 5 necessarily, because you can see 5 letters there, H, E, L, L, and O. But if it was a string, there'd maybe be like an end of string marker. Or it might be you're storing them UTF-8, so that's 2 bytes per character. And of course, you might have a RAID array because this is on the disk, or it might be some combinations of 5, 6, 10, 20. There'll be a different real answer, but it's important just to get away. 5 is unlikely and 6 is unlikely. The word hello, suddenly it's 10 or 20 bytes, which is not immediately obvious. Well, Hazelcast is fundamentally a memory store. So if you're putting that data in memory, what about hello? And how big is the Java string hello? And it might surprise you, it's somewhere around the sort of 60 bytes mark, because strings are objects. So there's a reference to the class, and then there's the fields. And I think in most cases, strings are implemented as arrays of characters, and it's an object that contains another object. So 60 bytes, which is even more surprising than 20. 5 letters becomes 20 bytes on the disk and 60 bytes in memory. And it's like, that doesn't seem obvious at first. But this is really important, because if you're doing sizing and you look at your data and it's like, well, we've got, we're going to store the names of 10,000 people, and the average length of a name is, let's say, eight letters, then that's 80,000. And it's like, yeah, we'll need 80K. And it's like, no, it's going to come out somewhere like 6 times that size. And it's like, that surprises a lot of people. And no, we haven't mentioned Hazelcast yet. This is just disks or memory store. How big is it going to be in Hazelcast? And when we put the word hello in a map, we by default store it in the serialized form, so the kind of flattened form. And how big that will be will depend on your serialization choice. So if you didn't know what your answer is to rule number 1, you're not going to be able to do sizing at this point. And that, how is it stored? There's a couple of config flags that will change how it's stored. So you can say store it serialized or store it deserialized, which will vary the size of the footprint. You can change the backup count. How many copies of that data record do you have? Those are runtime things because they're configuration. So you won't necessarily know that in advance. So any idea that you're going to do sizing, it's great to be able to do it. And the way we would recommend that you do it is measure it. Don't predict, measure. Because as we've just mentioned, prediction is quite difficult and measurement's dead easy. So you just insert lots of representative data and measure it, and the management center will show you how. So here's a little bit of code. It's just a loop, 1 to 10 million, and put the word hello into a map in Hazelcast. Now, those strings are all the same length because it's actually the same string, then that might not be true. But if we go to Management Center, what we would see, here's a screenshot. So we have no backups here because this is a test. And the storage format is serialized. So the string hello is sent to Hazelcast across the network in serialized format, and that's how it's stored. And 100,000 of those map entries takes up 1.2 gigabytes. So you can work out the entry, the key, and the value, and any metadata take up about 120 bytes. So that was a one node Hazelcast. So it doesn't matter what the backups are set because there's only one node. If we had backup count 1 and we add another node, we're going to need another 1.2 gigabytes. So backup count, just straightforward multiply it. If you store the data object as a Java object, so it's deserialized, so when you send it across the network, it goes serialized. When it's received, it's deserialized, returned back into an object, a structured object. It's too computationally expensive to calculate the sizing footprint. So it shows as NA in the management center, but you could always look at the heap size and get it from that. But obviously the heap size includes all the other stuff that's going on in Java. So there are Java tools that would allow you to snapshot the heap and examine the individual parts if you really wanted to know. So simpler way may just be put a lot of data in and just look at the heat usage. Gives you near enough. And in case where we did it here, it looked like it was about 1.8 gigabytes. So we're saying maybe, maybe 180 bytes. So summarizing rule number 9. It's not popular, if you're a developer and you have to say to your boss, we don't know how much we're going to need. But yeah, that's the truth. Very difficult to do sizing in advance. And the disk size does not, you're thinking, your boss thinks hello is 5, you're trying to tell him it's 20 or 60 because you've listened to this YouTube thing. That's not going to be a difficult conversation, an easy conversation to have. We tell them that it's wildly different from what you think it is. It depends on your development, which you maybe not done yet, and your serialization choice, your data. How are you storing it? Things that you can change while the system. You do a restart, and your memory is now bigger or smaller because you've selected more or less backups. And those other complications as well. If you put indexes on your map so you can query them faster. Just load some real data, representative data if you don't have real data, and measure it. Simple. So that's rule 9. Rule number 8, following rule number 9. Who spotted that? Boaz did. That's because I can see him smiling, or maybe he's just thinking Neil's stupid, can't count. Hazelcast is a distributed system. What that means is running across multiple nodes. So if you send a request in parallel, they might not come back in the order they came. So that's why rule number 8 is actually after number 9, just for a little bit of fun. So having said that sizing's not easy to get right, onto some other things. If you're using eviction, that will confuse people. So by default with Hazelcast, you put data in the map, it stays there. You can get Hazelcast to discard data on your behalf based on time or space. And that evicts the data from your Hazelcast instance. Essentially think of it as deletion. System activity. It will happen correctly, but it can look like it's incorrect. And that's why this is important to understand, that if you've gone for some systematic mechanism, it should be systematic and it will be systematic, but it might not look it. And then if you're like a user and you look at your Hazelcast and you say, oh, that's done, Hazelcast just done something random. And that is not good. That gives that misunderstanding, and your users will distrust the system you've built for them. And that again is not good. You just told your boss that 5 becomes 60, and then they're telling you can't even get eviction to work right. Time to be looking for a new job. So eviction, size-based eviction is you're deleting the oldest record. So imagine you've got your 3-node cluster. And the way you've inserted your data, node number 1 has got the oldest data record. So imagine you've put in data records 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So node number 1 has got data record number 1. It's the oldest, it's the first one you inserted. Node number 2 happens to be low on space. So node number 2 deletes data from node number 2. So node number 2 might have had record 2. So record 2 has deleted. So you've inserted 1, 2, and 3, and number 2 is gone. So it was the oldest data on node number 2. And this is a thing about the distribution, that's the absolute oldest data record is record number 1, but it's on a machine that isn't low on space. So there's no benefit to deleting that. Doesn't help node number 2. So if you look at that as a whole, if you do like a query, select star from, and it goes 1, and your user does a query select star from, and they see 1, 3, 4, 5, 6, 7. Oh, what's happened to number 2? And they might understand about eviction, but think number 1 should be the one that's gone. And of course, they'll start blaming things, and that's not a good thing. So Hazelcast has deleted the oldest on that local member, which is not necessarily the oldest. So typically on eviction, you want rid of the oldest, the least frequently used, or the least recently used. But as a whole, that can be a bit confusing. It makes sense once you understand, but it doesn't make sense. So the way Hazelcast does eviction is it's like a background thread. So to avoid pressure on the system, because there might be lots of things all evicted at once. And what it's basically saying is this data goes after a set period of time, not necessarily at the exact point, because expiry is a bit of a workload. So you want everything else to keep running without being impacted by housekeeping. So housekeeping runs at lower priority. So expired events are removed after. So the data goes when it is past its time. Not it's like, you know, got a sell by date, used before date. The data goes. If you're following Java caching standard, it isn't actually deleted. It's retained because that's what the standard says. So it's not returned to you, I think is the wording on the specification. And there's no expiry event because it doesn't expire until you actually then check it, and then it realizes the data is expired, and then you get the expiry event. So if you don't read it, you never get the expiry event. It's just the way JCache works, Java caching standard. So the thing to remember, eviction based on size is per member. So the one that's low on space is the one that deletes the data it has, not anybody else's data. An eviction based on time is per record. And you can have different expiry times on different data records, which adds further confusion. So if you look at it as a whole, it can be confusing to the end user. And that's where you get this danger of false alarms. So we don't want false alarms because people will think the system is not functioning correctly. You'll be viewed as a poor developer. You know, it's not good. So it's important to understand this one. It's not as critical as the serialization and the earlier things, but it is, you don't want false alarms. You don't want real alarms either. You know, it's false ones are even worse because nothing actually wrong. Well, maybe real ones are worse. You decide. We're trying not to have alarms. Let's go that way. You know, machine fails, Hazelcast keeps going because that's what it's built for. So rule number 10 is around quality. And what do we mean by that? So it's a data grid or a compute grid. You're storing data in Hazelcast or you're doing processing in Hazelcast. All the server members need to be equal. You know, when we said you've got 4 machines or 8 machines or 5 machines, remember odd is a better idea, then they all need to be the same kind of machine, because otherwise, if they're different capacities, if one machine runs fast and the other machines run slow, your data will work at different speeds. You get this record back quickly and this record back slowly, and that's really not what you want. The kind of guideline for a system, and I would almost stress it as much as to say it's a rule, is keep them all the same. You know, they've got to have the same amount of CPU, the same amount of network cards, the same amount of RAM. Everything should be the same for the service, because there's no kind of concept of a kind of more important server. They're all a team. Everybody's contributing an equal part, and they can only contribute equally if they've got the same setup. Clients are retrieving data. They don't have to be the same because it's just the one client. So client A and client B don't communicate with each other. So it doesn't matter if one client is faster than the other, but the client communicates with any of the servers. So it should be able to get a response back in the same time from whichever server it is using. So that's what equality is about. If you're getting hardware, make sure you get the same hardware. Same RAM, CPUs, desks. And it's important because when we do something like data backups, you put the data record to the primary copy and then to the backup. Well, if the primary copy is fast and the backup copy is slow, well, your change runs at the pace of the slowest one. So you haven't had any advantage to having a fast member if it's got to wait for a slow member. So have them all the same speed. Really, everybody should be contributing. You've got 1 million data records in 10 servers. Each server should have about 1/10 of the data, do 1/10 of the processing. Hazelcast, the way it routes the data, generally results in this. And when all servers are equally loaded, then they'll respond consistently to the client. You don't want hotspots and cold spots. You don't want one that's doing more than its share or one that's doing less than its share. Particularly true also for the network. If you've got different speeds between members on the network, well, that's the same. You want everything that you can the absolute same. Now, that's not always going to be true. It's true that you always want it. It just won't always be true that you get it. If there's a slight variation, that's going to be okay. So if you take that example down at the bottom, we've gone for 4-node cluster. That's a bad size, and then it's on 2 machines, which is another thing we don't like. And the reason you want each Hazelcast on its own machine is so it has uninhibited access to that machine's resources. It doesn't have to share them with somebody else. It means it gets consistent performance. But if you were doing this setup where you've got multiple Hazelcasts on multiple machines, then you've got maybe 2 on one machine, and those 2, because they're on the same machine, have very fast networking between them because it's not even going out of the machine. It's just running on the local network, local backplane, and going to one of the other Hazelcast instances is on a different network now and runs at a different speed. So it's not going to be good. Not necessarily bad, but definitely a thing to avoid if at all possible. So think of it like that. Your server nodes, they're all interchangeable. There's no one that's better than any of the others. This is particularly important when you if your Hazelcast has been running for a while and your business has got more successful, you need to scale up your Hazelcast, and you need to get some machines that are like the machines you've got, ideally identical. If they deviate, that's going to be a problem. If they deviate rapidly, wildly, that's going to be a big problem. So we've seen that go wrong for people. So just be wary of that. So the final 4, transactions kill performance. Transactions are great. I want to do some sort of update, and I want to update a couple of things, and I want them to be updated together. So I'll wrap them in a transaction, and that's my problem solved. And that's maybe your answer if you're a junior developer. Hazelcast is a distributed system, and to run that across multiple machines is transaction coordination. So transactions are kind of not intrinsically wrong. There's nothing wrong with transactions, but they have to do that machine-to-machine coordination, which essentially think of that as like putting the brakes on. If you want to win the race, you don't put the brakes on your car all the time. Certainly they put the brakes on at corners, but in other places, maybe not. So what we're saying is be careful with transactions. Nothing wrong with them, but if you want a fast system, don't then have the handbrake on your vehicle. So what's wrong with transactions, apart from performance? So if you're a junior developer, this is news to you that there's problems with transactions. Just go and have a look on Wikipedia, problems with transactional systems, or anywhere you like, or into your favorite search engine. You look for things like ghost reads and non-repeatable reads and all these things that can happen in transaction. It's all to do with isolation. And what we often hear is, well, I must have transactions. We're doing banking. It just cannot be wrong. And yes, we agree, it cannot be wrong. But that's correctness, not atomicity, and that's the thing that people kind of miss. So we'll kind of cover this quickly, what transactions are for that kind of banking problem, and how you might go about it without transactions and get a faster system. And at this point, we'll say you might not need a faster system, so transactions could be your way. So here's our banking example. We're going to move 100 currency units of whatever country you're in from account A to account Z or Z. So assuming you've got 100 to begin with. And really the business problem is, the balance of A needs to go down and the balance of Z needs to go up. And it's both or neither. You don't want one to happen and money has just disappeared out of the system, or worse still, has appeared in the system. And that's these two must both happen or neither happen, is a natural fit for transactions. But it's slow and correctness is actually suspect. And that's the part that you don't think, hang on, no, surely that's what transactions do. So this would be your business logic. You'd start a transaction, assuming A's got enough funds, you'd reduce the balance of A, increase the balance of Z, and commit the transaction, and the system sorts it out. And that's fine. So there's various problems with this. So while you're in the middle of doing this, imagine somebody said, well, what's the sum of the account balances? We can either do one of two things. We can either wait until that transaction's finished and then do the sum, the query, or we could do it while your transaction is running. And what we mean by a sum is like a scan, an SQL that says select sum X from map. So what does the scan see? So this is our starting position. Account A has got 100. There's various other accounts. They're all empty just for the simplicity. And account Z at the bottom has all currently got 0 as well. So we start doing a scan. We pick up, on our running total, we've found 100 from A. So our total running total is 100 from A. Meanwhile, the transaction then commits, changes the value of A to 0 and the value of Z to 100. And then my scan reads the value of Z and gets 100. So I read 100 from A. My cursor is moved past A. The transaction commits. My cursor gets to Z and reads in the 100. So I've seen 200 in my select sum statement. So if I do, this is called read skew. If I'm doing a query while I'm doing a transactional update, the transaction has done the right thing and my query's got the wrong answer. 200. Correct steps on correct, consistent data has given an incorrect result. So that was the transactional way. We don't want anything to see the data until it's changed in both places, and that's fine. But if it's examining multiple records, it might read record A before and record Z afterwards. And actually in this one, it wouldn't be any different if the transaction wasn't used and it just did up A and B one after the other. So transaction does not mean correctness for everything else that's going on. So don't think of them as magic. They do a lot of good things, but they're not without problems. And so we know that they're not without problems, and we know that there'll be that networking liaison between processes, which is going to be slow. Oh, well, is there a better way? And maybe. So we want A to go up and B to go down, or sorry, A to go down and Z to go up. Mr. B nearly got some money. And it's 2 updates, but we do it now as 1 data record. So we insert an event into the system, which is At 216, we want the event is we move this from A to B. So we don't update we don't store the total on A, we store the difference record. Oh, how have I gone? I've grayed out. Don't know what happened there. So if we do what is the balance of A at 215, then it doesn't include that record. If we do what is the balance of Z at 215, it doesn't include that record. So that's two independent requests that get the correct result and the consistent result. If we do what is the balance of A at 217, then we know that 100 has been removed from A, and we can tell you that the answer is 0. And if we do the balance of Z at 217, we know that 100 has been added at 216. So we can insert that one data record and a query that says, what is the total at 216? What is the total at 215? Gives us the correct answer. So it again is a either or both approach. So that non-transactional way is basically you have a way of giving a starting balance, and then all the deltas essentially since. So there's our transaction worked in a different way. If I do my query, select sum of balance at a particular point in time, it either includes that delta record or it excludes that delta record and gives us a consistent answer. So you can have a consistent answer, using the timestamp-based approach, or you can tolerate that you might have that intermediate position, just doing the ordinary SQL, select sum, you choose. And now you're aware what the difference is. I mean, in a moving system, if you want to say what's the total of what's going on, well, you probably would want that consistent. So you would use the select timestamp, but it might be that that there are no operations going on because it's outside business hours, and then you could just do the simpler version. You're choosing. So how does that help with performance? Well, it helps with performance as well because you don't need to lock the data records you're changing. You don't need to change them, and you don't need to unlock. It's just a single insert. And it's not an update. So if you've got journaling data structures, it's even easier. So summary on transactions, they are not magic. You need to be aware of their fundamental flaws. Those are not bugs. They're just the way they can only ever work. They're going to be a bit slow because of the cross-network coordination. And you will need them for some things. What we're really saying here is just don't use them without thinking. Transactions are perfectly fine, but they're not a free lunch. You've got to accept their downsides, which are performance and that consistency issue. Number 12, last three. Code your pipelines carefully. So in stream processing, there's a classic introductory problem is word count. So if we had Hamlet speech, to be or not to be, how many times does the word the occur? How many times does each of the word occurs? And it turns out, at least in that snippet, that the word the occurs 3 times, and be occurs 2 times, and to occurs 3 times. If you were coding that in a stream processing pipeline, this might be how you would do it. This is correct. This gives you the correct answer. Tests will pass. It is the correct answer. Or is it? So there's a mistake in this, deliberate mistakes. You're doing very well if you're spotting this and you haven't hit replay to go back. I'll give you a clue. Now can you spot the mistake? And what's wrong is we are taking the word and turning it into lowercase. That's so that the at the start of a sentence gets counted with the in the middle of a sentence. And then we're discarding words that are less than 2 letters. So we'll count 2, but we wouldn't count a or I. And what's wrong is it's inefficient to transform a string to lowercase to then discard it based on length. So it would be more efficient to do this the other way around, fractionally, fractionally more efficient. But if you're processing billions of events, as we do in Hazelcast, then it makes a difference. So just be careful. So maybe what we're kind of saying here is unit tests and so on will find a lot of errors, but not necessarily all things that are incorrect, because this is a very subtle incorrectness. It's going to give you the right answer. Just a different way of coding it gives you the right answer faster. So there's the answer. You convert some data to lowercase and then discard it. So the kind of rules for string processing is really, don't do that. So it's around projection and selection. So if your data record is big, then projection is make your data record smaller by cutting out fields you're not interested in. And then that moves faster through the pipeline and get rid of any data that you don't need as soon as you can. The general rule with big data is big data becomes small data. Stream processing normally has, drinking from the fire hose, as the expression is, and you've got a huge flood of information coming in that you need to filter down as quickly as you can to get through it at high speed. So that's if you want to code it. If you can write it as SQL, then it's back to the technical debt. If you remember that Lambda, when that first appeared, it was like, whoa, that's when we moved to Java 8 and Lambdas came in. It was quite a struggle to kind of get our heads around it. And that's always going to be the case for anybody who's new to the team. So if the code's difficult, we'll do it in SQL. SQL has, query optimizer. It might end up doing a better job than you. Might not. Depends. Query optimizer is not always going to be able to spot things that maybe you can, because you're aware of some facet of the data. So if you can, try it both ways. If they're about the same, then the SQL way has got lower technical debt. Everybody can look at the SQL and get a rough idea what they're doing, whereas Java pipeline, you need to be pretty decent with your Java. So if you can do it as SQL, fine. If we went back, I don't know how long you looked at that pipeline, and if you spotted it before I highlighted the two wrong lines, maybe you did, maybe you didn't. I can tell you for sure that you wouldn't spot them all the time, and that's the thing. So it can be difficult to spot those optimizations. On to rule 13. Garbage collection. You can fight it, but you're not going to win. So Java is getting better and better. Java 8's garbage collector isn't as good as the one in Java 11. If you're using Java 8, you should upgrade. The one in Java 11 isn't as good as the one in Java 17. You can get the theme here. And the one in Java 17 isn't as good as the one, and these are going to continue getting better and better. So, upgrade your Java when you can, and you'll get better garbage collection. But you'll still get garbage collection. Just less of an impact on you, but not zero impact. So when we were talking earlier about sizing, one of the things we said is, it's very difficult to do the sizing, but suppose you've done that, loaded in a bundle of data. You can't put 10 gigabytes in a 10 gigabyte heap. How much space do you need? And kind of, if you had to guess, then 2/3 full is a good starting point. So if you had 8 gigabytes of data, that might be a 12 gigabyte heap. A 12 gigabyte heap for 11 gigabytes of data, it's got almost no headroom. That would perform badly. A 12 gigabyte heap for 1 gigabyte of data has got a huge amount of headroom. That's wasteful of resources. And they're not free. So that's probably not great. So that's why maybe 2/3 full is a good kind of starting point. If you know nothing else, 2/3 full on heap size. but it's a starting point, because garbage in Java is generated when you're changing data records and things. Here's the new data record, the old one is now dereferenced, and it's garbage. So if you're doing a lot of updates, you're creating a lot of data records, you're creating garbage from that is the previous data record. So your pattern is maybe heavier towards garbage collection than if you're just doing reads. So some applications are kind of more on the reads and hardly ever change the data, so generate garbage at a low rate. And other, so if you imagine something like your online banking, your transaction history doesn't change. So you might read that many times, but hardly ever insert, because you're only ever using your bank card once every so often. So that data would have a low garbage footprint compared to something else, perhaps, that's changing its data more frequently. So your tuning, if you're going to do tuning, kind of needs to accommodate your application pattern. And it's not like a one-off. You really should be doing it recurring, because what will happen is somebody will introduce a new feature in your system and it will behave in a different way, So you need to review your tuning. And really, you need always, with the tuning flags, to know why did you set them in the first place. You need to keep a history. Nothing worse than just going in and seeing some flag that's set to true or false or whatever. And it's like, why did we do that? And, the person's won the lottery and left, and we don't know why. And you still get in touch with them, but would you trust an answer? So heap size, couple of simple things. Set the minimum and maximum heap size to the same, so you get all the memory you need when the JVM starts up. Because otherwise, before trying to grow the heap, it will do a garbage collection to try and avoid growing the heap. And if you get all the data, all the heap you're ever going to need at the start, then you can avoid that. Also, there's little tricks that may be going on with memory stitching. So if you try and grow 8 into 12, you might get another 4, but it will appear next to the 8, but it actually is in a different part of the machine. So it gives you a little performance speed bump. So if you've got a continuous 12, because you requested it all at once, that might perform slightly better. So go for all the heap you can get at the start. And if you don't get enough, then your JVM fail to start, fail fast, that's good. How big? And don't know. We've seen places have had problems with 20 gigabyte heaps. We've seen places that have been running 32 with no problem at all. So it just depends. What we can kind of tell you is that the pain of garbage collection is bigger, the bit more it's got to look at. Bigger the heap, the worse it is. If that's a problem, Hazelcast has sells an off-heap storage solution where you move data off the heap. You can make the heap smaller, garbage collection kind of goes away. So you just keep the heap for transient information. So there are answers. I mentioned about the tuning. The last time I looked, there was 700 tuning flags. And it's like, whoa, imagine if you were called into support system and we've set 145 tuning options. And it's like, that's back to what I said earlier. You'll never achieve that perfection. Just try and get, 90% perfect or whatever. And I mentioned about the billion events that we processed. When we did that billion events per second benchmark, we only used one flag. So you probably don't want many tuning flags. I would have said if you've got maybe 3 is like a warning, that's like an alarm bell. If you need to change more than a couple of tuning options, something fundamental is wrong. You've made your heap too big in GC straining. You should make the heap smaller and maybe have more processes in your cluster to make sure you get the same capacity. So if you want to do GC tuning, turn on GC logging and get a GC analyzer to tell you what those flags are. We have seen 1 or 2 tuning options make a big difference. several, it's that frog on a lily pond thing that it just makes fractions and increases the technical debt. So 3, I'm saying that's a warning flag, as in like a warning flag to human being, not a JVM flag. So it's like, yeah, this system's struggling to keep working, and they've had to tune it to death to get it to achieve its goals. That's the wrong way to go about it. Just add some more processes. So here's our summary here. Use the latest garbage collection. Use Hazelcast off heap if you can. And tuning is, it's not an exercise you really want to do, but if you do it, you just need to keep doing it. Make sure your system stays in tune. If it's not doing any kind of self-sizing, then a value you set might become wrong over time. So a little tuning is worth doing. Make a huge difference. A lot of tuning, bad.